Hi, my name is Dave. I go by the name Dave Makes Stuff online and in my design portfolios. I do a lot of design work for the 3D printing community, and I use nTop quite a bit in those designs. This is one of my recent designs here that's got some attention, and so I thought I would do a tutorial about it. It's sort of an abstract tree, Christmas tree looking design, but a lot of questions about how I do this texturing right here. And it is done in nTopology using fields. And fields are a fascinating component of nTopology. It's a way of creating essentially a numerical value for every point within your three-dimensional design space. And then you can use those values. You can manipulate those values mathematically, but then you can also use those values to modify your model in a whole range of ways. So very useful in terms of field-driven design and lots of engineering applications. Also very beautiful, which is what I like about them. So here's, I'm just pulling, I'll talk more about these fields. This is the field viewer, that colorful thing that you can see me pulling up there. And I just wanted to show you how this larger field that permeates the entire design space is being used to modify the surfaces of that tree there. So let's back up a little bit here and a little bit about these trees here. I'm calling them the Lawren trees, and that's just because the style reminds me, and it's inspired by the work of Canadian painter Lawren Harris. This is one of his more famous paintings. It's Mount Leroy. I just love the abstract contoured surfaces that he uses in the painting, and he does some. There's some paintings of trees as well that I think look sort of similar to the design that I was making there with the contoured tree. If you're not familiar with nTopology, I encourage you to take a look through the website. Lots of information on here. It really is a program designed for high-end and engineering applications. I tend to use it more for art and creative applications, but I think that some of the things that I do you might find helpful no matter what application you're using nTopology for. nTopology also has a great nTop Ed community where members can post questions and resources, and anything that I share here in this tutorial will be posted here for those who have access. I will post the original files and all of my nTopology files here for you to dig into a little bit deeper. If you don't have access to nTopology and you just want to print these designs, they are free to download from Thang's my profile page on that, and the link will be below. And those STLs can be downloaded here. There's 3 different sizes with 3 different unique contoured surfaces on there. So let's get back to this design, the design here. So let's just close this out. And first, I want to give you just an overview of this. This is the main program that I'm using, but at the top here is a custom block, which is a wonderful feature of nTopology. It lets you nest complicated functions within other complicated functions. So there's a custom block here that creates a seamless cylindrical field that I will go into separately, and then that field is used to modify just a regular cone there. So here we have, let me just close that down. So there's the base right there. So that's the modified cone that's been modified by the field that I've created there, and then there's a way of sort of inverting that field, and then I've just applied a different color to it there. So we have 2 fields that make up the tree. So starting at the top here with this cylindrical field, and I'm going to actually open up another instance of nTopology here because this is a whole thing in and of itself, and it's a custom block that I developed for a few of my designs, and I think there must be some other application for it out there because I find it really helpful when I'm using these simplex noise fields and applying them to cylindrical objects. And I'll tell you why that's important. So here, if you look up here, this is my basic, I call it the origin noise. This is the basic simplex noise function that I'm inputting into this custom block. So random seed is just at 1 and the frequency is at 2. For those who aren't familiar with how these fields work, if you increase that number, it just makes the randomness more dense, and then if you put a lower number, it makes less dense sort of randomness in there. So I find that 20 is a good function for that. Now down here, I've got so I've just created this cylinder. So basically, we're going to use the values within this noise field to offset the surface of this cylinder here. So what I want to show you is if we take this origin noise, this basic noise that's spread out throughout 3D space there, and we input that into the remapped cylindrical field block, what that looks like is this. And you can see there's a big seam in there. And so that when we use that cylindrical noise field and apply it to a cylindrical object, we get this big ugly seam. And no amount of smoothing or messing around can get rid of that seam. It is just there. So that was a challenge that I encountered early on, and I wanted to find a way to fix that. And a sneak preview here. Here's what it looks like after using my Seamless Cylindrical Fields custom block here. So let's just give you a quick summary of what that looks like. So what you need to know about these the remap cylindrical noise block is how it does what it does on a basic field. So you can see there's a Y mapping length that is an input into the remap cylindrical field, and you can see it down here at the bottom. The Y mapping length, I've just used the variable there to pull in the value of 20 millimeters. So what that is it's a distance. It's in the Y direction here. From half of the Y mapping distance, so in this case it would be 10 millimeters above the origin point to 10 millimeters below the origin point. And basically that whole line there is when it's remapped into the cylindrical field, that is compressed down into a single point. So everything in the positive X direction between, within that range there, everything in the positive X direction becomes radial, becomes emanating out from the point. So what that means is all of this stuff above the that point of 1/2 of the Y mapping is not included. Anything in the negative X is not included, and anything here below that 1/2 of the Y mapping length is also not included. So it's only things in this area that then become, this is compressed down to origin, and everything else is shot out basically as in the radial, in the radius there. So here's the trick that I came up with. So here's the origin noise, and now the second block here is shifted noise. So all that I've done is I've shifted this origin noise, and I've shifted it down. So you can just watch that a few times. There's the origin noise, and it's shifted down 20 millimeters. What that lets me do now is to actually mix those two fields, so that because what we essentially want is the bottom part of that X mapping length to be the same as the top part of it, so that when they are circled around in the remap cylindrical field and essentially come into contact with each other along this side here, they are the same. So what this piece does here is it uses the mix block to go from scalar field A, which you can see here is the origin noise at the bottom, and up to the shifted noise at the top. And basically it's you're going to have to dig a little deeper into this block when you upload it, but it's going from 100% origin noise at this bottom part here to 100% of the shifted noise, which is the same because it's been shifted. It ends up being the same. I'm rambling on here a little bit. You don't have to understand the details of it, other than I want you to compare what that looks like. There's with the seam in it, and then right there we've taken that seam out, and there's a seamless connection of those cylindrical fields, which is what you need when you're using, especially when you're going for something aesthetic, and you don't want those seams to be appearing along your piece. So there's the long explanation of what this custom block is here. We've returned back to the notebook with the tree in it, and at the top here is the cylindrical field custom block. So there's a few different things that I just wanted to show you here. So this custom block, as I have it set up, and as I will put it up on the nTop community page, it will input any field. So I'm actually inputting a modified simplex noise field in here. It's a remapped scaled noise, and the reason for that, let me just show you the. So here's what the regular basic inputted noise looks like, and then I have remapped that like that, and I've scaled it. I've scaled it here, and I can show you what these numbers do here. So the Z scale at the bottom is basically the amount of droopiness that I want this to come, to go along the Z direction down the object. So you can see if I go from 50 to 5 and then let regenerate, that it doesn't look much like snow anymore. It's just a bit too jumbled up there. That looks really cool. That might be what you want in some applications, but that's not what I was looking for. The X scale here, you can see I've rescaled that to a scale of 500, which means I've really stretched it out along the X. And why I did that is because if you remember the positive X direction here, when it's put into the remap cylindrical field, that turns into the radius. So if I've got that too low, let's put that down to 5. If I've got that too low, basically what happens is it just gets too scrunched up, and you can see there's all these waveforms. They're just too tight, and that's not going to print very well. It does look kind of cool, but it's just too many condensed waveforms, radially up against that offset surface. So that's why I've got that pulled right far out there. It just gives a nice smooth surface on there. So that is the cylindrical field input. These right here are my variables to create the form. So it's a cone that's 140 millimeters high, and I've actually got it half the diameter, 70 millimeters. I find that works well. And here's the offsets. We'll talk about that a little bit later. And there's the period, which is affects the number of ripples here. So this is where the fun happens as well too. So let's just remember what this. So here's the cylindrical field. Looks like that. So that really doesn't look like much. And if we put the probe values on, we can see what these different values are. So near this reddish magenta kind of, we've got a negative 0.3. As we come to the black here, we've got a positive 0.3. And then that just varies cylindrically in a circle around there. So what I do with that, because I want to have all these values in the positive for the next few applications, I use an absolute value block there, and so we can see it's got the same variation, same peaks and troughs, but everything now is in absolute values. This next block here, so let's just remember here, when at this point these are unitless. Every point has a numerical value, but it's a unitless numerical value. What I do next here is I times those numerical values by 360 degrees. And it doesn't change the look of it at all, but at this point here, we've got close to 0, it's 5.8 degrees, and then over here we've got a larger number of degrees. And the reason I'm switching things into degrees, just to give you a heads up, is that we're working towards a trigonomic function here. I'm going to be using a sine wave or sine function to get these really funky waves here. So you could do this in radians. I find it easier to do it in degrees. But I have to create this field space in degrees so that I can use that sine block there. So right now, I would just have, if I used a sine function on this field right now, I've really only got degrees ranging from 0 to 360. I would just get a single wave, bouncing around in here. It wouldn't look all that exciting. So when I multiply it here by the period, and I've got the period of 6 right here, that is just going to create multiple sine waves in that space when I apply that function. So again, we're visualizing this field. It doesn't look any different, but now you can see that the values here are ranging from around 0 degrees here to all the way up to over 1,000 degrees up here. So now when I put that field into a sine function, I'm going to get a whole bunch of different waves. And this is my favorite part. Wow. So that is essentially putting 6 different sine waves between values of 0 and between the lowest value and the highest value. So now you can start to see this is starting to look a little bit, the field here is starting to look a lot more like that offset surface that's on the trees. And if I drag that up, we can see it changing and morphing at different points there. So that to me is the magical part there. In this current form, again, this is coming out of a sine function, so I've got unitless values in the field right there. You could offset a surface negatively and positively, so I could just use this directly to do the offsets, but I find it easier to control if I'm just working with positive offsets. So here I use this linear map, and you can see the in, min, and max are -1 and -2. So I'm taking values from all of this field, and I'm remapping that to 0 and 1. So now if we look at that field, I've just taken out all those negative values, and everything here is ranging from close to 0 there to the dark points are close to 1 right there. So things are cleaning up, and then I add in one more multiplication block here, which is going to add the units, the millimeter units, which then can be used to directly offset the surface. So let's just take a look at that. Again, that doesn't change very much visually, but now when you can see, I've got the probe values on here, and now you can see as I'm moving around within the field here that these points here that aren't being offset much, you can see that's a sort of a valley in there. They're not being offset, so that's close to 0 millimeters. And then these points out here are getting a little bit higher values there. So, but you can see I'm when I offset this body, I'm not simply offsetting a a consistent amount. And that is because you can see at the top here, there is no offset, and at the bottom here, there is lots of offset. So the offset is a gradient from the top to the bottom, and I'm using a ramp field here. So the ramp field is driven by the cylinder that runs down the middle, and right, so you can see the in min, so right up next to that cylinder, that matches to the out min, which is 0 millimeters, and then on this the in max, so at any point 28 millimeters out from this cylinder right here, that's when we're going to be offsetting our maximum offset, which is just this variable here, which is 3 millimeters. So that is how I created this this gradient of offset from the top to the bottom, and that's really important. If you have 3 millimeters of offset at the top there, you can imagine that's just a big cluttered part there, and it doesn't render or print very well. So that in a nutshell is how the this base file is, or sorry, the base tree is made. I'm actually just going to go to the to these ones here. The assembled ones have the bottom trimmed. This set here doesn't, and I wanted to do that just to show you how I created the snow. So that happens in this part of the this piece here with the linear map, where I'm taking that noise field and I'm mapping values of -1 to 1. I'm mapping that to 0 to 1. So remember that, 0 to 1. All that happens down here with the snow accent is that I'm basically mapping those fields opposite. So that field that again is from -1 to 1, or sorry, -1 to 1, I'm now mapping that from 1 to 0, right? 1 to 0 there, 0 to 1 there. So it really is just the it's just the opposite, and I've colored that a little bit differently so you can see those two forms being opposite there. So I enjoyed that. I know it's a little, it gets a little overwhelming for such for something that looks fairly simple, but you know, as you get fluent with nTopology, all that stuff makes perfect sense, and it's such an elegant way. These fields are such an elegant way to create some really complex textures and forms that are really quite beautiful. So. Again, you can go to my page here and download those files, and all of the programs here will be included in the nTop community section. I hope you enjoyed. Thank you very much.